Get started. It's possible not everyone's here, but since we have so much to cover, this is hopefully season 5, the finale. And today we will continue to talk about how to build a SNARK. We've already talked about all the applications and definitions. And last time we had already started building a SNARK. We started building what was called the Killian SNARK. The Killian SNARK being a very simple one, but inefficient, so that it's not actually used in production anywhere today, but it's very easy for us to understand, where we started with an argument of knowledge, made it succinct, and then made it non-interactive. And to recap what exactly our system is, we're trying to construct a SNARK using 3 components: the setup, S, prover, P, and verifier, V, such that the prover takes as input some public information, X, some private information, W, also known as the witness, produces a proof, pi, that the verifier takes as input along with the public information, X, and decides whether it should accept or reject the proof. Completeness is a property that says that if the prover knows a correct witness, the verifier should always accept. And proof of knowledge is the second property, which says that if the prover does not know a valid W, the verifier should accept with very, very small probability. We talked about the PCP theorem, or the probabilistically checkable proof theorem, which says that for any circuit, there always exists some proof system that satisfies these criteria. And the proof system works by sending a proof of size almost the length of the circuit, maybe more. The verifier spot checking that circuit, and then each bit that the verifier spot checks being correct with 50% chance if the prover is dishonest. If the prover is honest, each bit will always be correct to the verifier. And that way, if the verifier checks lambda of these bits, the verifier will accept a fraudulent proof with very, very small probability as lambda goes to infinity. And this is sort of a diagram. The prover generates a long proof pi. The verifier spot checks a few of these bits, and it, as a result, will output accept or reject. We said that that was not succinct because the entire proof has to be sent over. So we make a Merkle root from the proof and then send the Merkle root over instead. The other thing was to make it non-interactive. And in order to do that, we have the prover generate the randomness that is used to spot check instead of the verifier generating the randomness. But we do it in a way using the Fiat-Shamir heuristic so that the prover has only one choice of how to generate the randomness and can't cheat. The way the Fiat-Shamir heuristic works is that if there is some dialogue required where randomness needs to be sent from the verifier back to the prover, here the prover just generates the randomness themselves, but they must commit to the randomness by hashing as part of the procedure the message that they had planned to send to the verifier first. That way the verifier can tell that the prover didn't change their message after they found the randomness they wanted. And so that was the conclusion of that. We talked about how the Killian SNARK is not used in practice, but that is because it's inefficient running in cube time of the size of the circuit. Also, it is not zero knowledge. So to build an efficient and possibly zero knowledge SNARK, we have to start with a different direction. We first convert the circuit into a rank 1 constrained system. Then we convert the R1CS into a linear probabilistically checkable proof. And then we compile the linear PCP into a ZK SNARK using a trusted setup. Remember that trusted setup means that the setup algorithm, the randomness it produces, needs to be hidden from the prover if it's meant to be sent to the verifier, because if the prover could see the randomness that the trusted setup used, then it would destroy the SNARK's security. The other path is if we want something that's not with a trusted setup, we can convert the R1CS program into a slightly more complicated linear interactive oracle proof, or IOP, and then compile the linear IOP into a transparent SNARK, which is a SNARK where the randomness created by the setup algorithm can be seen by everybody, and the prover seeing the randomness doesn't affect anything in terms of its ability to cheat. So we start with the construction of the rank 1 system, which we did last time. R1CS programs are another way of representing an arithmetic circuit. So they're another way of representing like a program that tries to prove some fact. Arithmetic circuit evaluating to 0 is one way to prove a fact. In this case, to prove our fact with our R1CS program, we define 3 matrices, A, B, and C. We, again, have X as our public information, W as our witness, and we define them along a finite field that we'll talk about M in a moment. Given the inputs, X and W, just like with the arithmetic circuit, the program, the R1CS program would output 0 if this relationship over here is true. The matrix A times this vector Z. The Z is called the input vector, but it's really just a 1 concatenated with X and the W. So why is there a 1 in the front? We'll talk about that in a moment. But this first matrix times Z, matrix multiplication with the second matrix B times Z equals the third matrix C times Z. If this equation is true, then the R1CS program outputs 0. So to try to prove a fact using R1CS, we want to evaluate this, whereas with the arithmetic circuit, we wanted to evaluate this statement up here. Some more vocabulary was that, yeah, the Z is the input vector. A, B, C are matrices expressing M constraints. So these are constraints that the R1CS program has to satisfy. R1CS stands for rank 1 constraint system. Rank 1, we're going to talk about in a second, means that everything has to be able to satisfy this form where there's like one term multiplied by a second term, and it's like a linear combination of multiplications, but nothing more than one rank of if you took linear algebra, nothing more than one rank, meaning that there's no like quadratic or cubic or other operations involved. And I told you that every arithmetic circuit can be written as an R1CS program, where you just set M, the constraints, to be the number of multiplication gates in that circuit plus 1. And so then we gave you an example of how to build an R1CS program, not yet converting a arithmetic circuit into one, but just to build an R1CS program. This R1CS program is to try to accept the fact that is X being between 0 and 2 to the D for some power of 2. That means that if we were to build an arithmetic circuit, we would also want like the arithmetic circuit to return 0 if X is in this range. And so we saw that if you wanted to build an arithmetic circuit for it, you could build it this way, where you basically have a bunch of factors. Each factor is X minus some integer between 0 and 2 to the D. That way, if X equals any of these, then this entire expression will evaluate to 0. And if X is not within this range, then this entire expression will not equal 0. For the R1CS program, again, we need to turn it into some matrices A, B, and C and stuff. But more importantly, we need to be able to turn this into a set of constraints. So we got to think about constraints first. In order to constrain X to be within this range, let's represent it using binary. Represent it using a set of bits W1 through D, where each of the W1 through D can either be 0 or 1, so they're a bunch of bits, such that X is equal to the binary representation of itself, where each W is raised to some power of 2. If there exists some W's such that this equation is true, then that means X must be within this range 0 to 2 to the D. If X is greater than this, then these bits are not sufficient to represent X, meaning that this constraint would be unsatisfied. And so we were able to construct that constraint, which we reorganize in A such that everything is moved to one side of the equation and is multiplied by a 1. And we need D other constraints. So D other constraints are to constrain these bits W1 through D to be 0 or 1. If we didn't include these other D constraints, these other W bits could theoretically be any values in the finite field, but here we are explicitly telling them that they can only be 0 or 1. Because if they're not 0 or 1, then this constraint will not be satisfied. Then we're able to define our input vector as 1 appended to X and appended to these bits W. And so it has length D plus 2. So given that there's D plus 1 constraints and there's D plus 1 variables in our input vector's length D plus 2, then we can take these constraints and turn them into our matrices, A, B, and C. Our matrix A will take all the coefficients that belong on like the left half of the term. So notice that for each one of these expressions, there's a term on the left that is a multiplication with a term on the right, and it equals something on the right side of the equation. Term on the left, term on the right, and then right side of the equation. So A takes all the coefficients from the stuff on the left. So here, is there a 1 in the expression on the left? There's no 1 over here, so the coefficient will be set to 0. What is the coefficient for X? It's -1, so A will take a -1 here. The coefficient for W1 is going to be 2 to the 0, which is 1, so it'll take a 1 here. W2 would be 2, W3 would be 4, all the way to WD, which is 2 to the D minus 1. So you see for this first constraint, A takes these coefficients. For the first constraint, B takes only the coefficients for this term right here, which happens to just be a 1. So B takes a 1 here and 0s for everything else. And then for the rest of these constraints, A will take as coefficient 0 for everything except for WI. WI being the ith bit, it'll have a coefficient of 1 out here. So 1 over here for W1, 1 over here for W2, all the way down to 1 over here for WD, which means that it's a identity matrix over here in the bottom right corner, and there's zeros over here because X and 1 don't appear in the left term. B looks at the right term and sees that, is there a 1 that appears? Yes, and it has a coefficient of -1, so there's -1s every here, every row over here. X doesn't appear, so there's zeros over here. And then again, there's an identity matrix of 1s for the WIs over here. And then finally for C, what is everything on the right-hand side of these equations? It's always 0, so C can just equal 0. And so in this way, we've turned our constraints into a set of matrices A, B, and C. And that way, when we multiply them together, this equation will only evaluate to true if X is actually within the range 1 to 2 to the D. Sorry, 0 from 0 to 2 to the D. And that's where we stopped last time. So questions?
This was just like a notation question. If you go back maybe a couple slides to where you define like A times Z composed with, yeah, here. So there's like that small dot operator, and then there's that like that dot with this with the hole in the middle.
Yeah, so the difference here is actually A times Z is matrix multiplication. Meaning that like, since Z is a vector and A is a matrix, you'll multiply Z with every like row of the matrix, and then that will be concatenated together into its own vector. This is element-wise multiplication.
Okay, gotcha.
Meaning that it will not like do matrix multiplication, it will just take each element in the same position for this term, and then multiply them together. But it won't do any sort of like matrix multiplication where you're like taking a row and multiplying against a column or anything like that.
Sweet, thanks.
Cool. So now let's go on to the second example. And this is an example of how to convert an arithmetic circuit into an R1CS program. So let's take a look at the right-hand side over here. This is an arithmetic circuit, like the ones we know and love. This circuit in particular expresses a relationship that's x1 times x1 plus x2 times x2 times w1 plus x1 over here. Questions about how this circuit works? So this is just a circuit like we've seen before, and this is what it looks like. And now if we're going to turn this into an R1CS program, we have a couple things we got to do. The first thing we got to do is we have to label each multiplication gate using a W variable, just like we talked about before. So now on the right-hand side, you see we've labeled this multiplication gate with W2, this multiplication gate with W3, and this multiplication gate with W4. So we're going to treat each of these as some sort of new variable, W. And in particular, we're doing that so that we can break down this big expression, which is not rank 1. This expression is much greater than rank 1, but we can split it into several equations that are rank 1. So meaning that there's only one multiplication involved in each of them. So this way we can say x1 times x1 plus x2 equals W2. And then we can say that W2 takes the place of x1 times x1 plus x2 everywhere else in these equations. In particular, W2 will appear down here and W2 will appear over here. We can also say that x2 times W1, which is this expression over here, equals W3. That way we can use W3 everywhere instead of this product. And so then when we get to this multiplication, we have W2 times W3 equals W4, which is exactly the same thing as what this expression over here was, except that now you have a bunch of equations with only one multiplication involved. And then finally, we have W2 plus W4 times 1 equals 0. So that this ultimately, this big expression has to evaluate to 0. The circuit has to evaluate to 0.
One thing I'm trying to get is there's that extra plus x1 in the circuit definition.
Oh,
but I'm not.
actually, this is actually not, sorry, this might be a typo. I think this is actually supposed to be x1 times x1 plus x2. The way you can trace it is that you have this whole expression down here, which these are all leaf nodes that get pulled into this multiplication node. And then this node, you see how there's an arrow drawing it to this multiplication gate, but there's also a separate arrow drawing it to the plus gate. And so you can say that everything inside this little subtree will be added to whatever comes out of this arrow. And so
Cool.
what exactly is in this subtree? It is x1 plus x2 times x1. So this actually over here is a typo. It should be x1 times x1 plus x2. Over here is actually represented correctly because we write it as w2. w2 plus w4. This whole thing over here is w4, and this thing over here is w2.
Sweet, thanks. Yeah, makes sense. And then what's the point of that times 1?
The times 1 here is we technically need every one of these equations to have a multiplication, exactly one
Okay.
multiplication, so that then we can
Gotcha.
use the matrices A, B, and C.
Okay.
So then this system of 4 constraints over the inputs 1, which is our scalar, x1, x2, and w1, which are the ones that we actually specified in our arithmetic circuit, as well as w2, w3, and w4, which are introduced when we're converting it. This whole system can be expressed as an R1CS program with some matrices here. And in particular, what are the sizes, the dimensions of the matrices? It is 4, which is a number of constraints, by 7. 7 being the number of variables in our input vector, 7. I'm not going to actually build the arithmetic circuit for you just because, sorry, the R1CS program matrices for you just because we already did that exercise, but please ask me questions if it is confusing how to turn a arithmetic circuit over here with these with these multiplication gates into an R1CS program. Yeah, as you can tell, this is just a sort of like a bunch of math, really. You're like, how is this getting us any closer? You know, we've just like expressed it in an equivalent fashion, except now instead of a circuit, we have just used a bunch of matrices. The key is not so much in the expression of it as matrices. The key in it is that now we have a form that is something times something equals something. Whereas before, our circuit was like a bunch of random operations equals 0. Now we have something times something equals something, which you'll actually realize in a moment is very, very good formatting for how to represent transactions and the state of the blockchain. So now we're going to go to step 2, which is we want to take this R1CS program and turn it into a linear, probabilistically checkable proof. All right, this is where things are going to get even more intense. So please ask questions, and you have the copy of the slides from the Discord so that you can go back and reference things if I'm going too fast. So what is a linear probabilistically checkable proof? Recall that we had a probabilistically checkable proof that we didn't say was linear before. And before, when we talked about that probabilistically checkable proof, it was that you, as the prover, would generate some proof that might be really big, might be the size of the circuit, right? But we turn it into a Merkle tree with a Merkle root. We send that Merkle root over to the verifier. The verifier then spot checks some positions of the proof by asking the prover to send those bits over. The prover will send those bits over as well as the Merkle proofs for those bits so that the verifier can be sure that these bits that the prover is sending over did actually belong in the original proof. And then the verifier will check each of these openings or each of these bits and then decide whether it wants to accept or reject. And so it's like a probabilistically checking proof. Again, it's interactive, and as a result, it can't be a SNARK on its own, but it's related to what we're going to talk about, which is a linear probabilistically checkable proof. It is another category of PCPs. It's actually a slightly more special case of a PCP. This is how a linear PCP works. First, a prover will send over some proof, just like before. And here we're just going to break that proof down into all the little bits in its string. So there's L bits in its string. Okay, so the proof is of whatever length L, and each of these pi1 through pi L is just one of the bits in its string. The prover sends it to a verifier, but here we're going to split the verifier up into 2 sections, verifier 1 and verifier 2. Verifier 1 will receive this proof, and verifier 1 will send a query, but this query is actually going to be of length L. So instead of sending like like a few bits of randomness, like lambda bits of randomness, the verifier is actually going to send over a query that is like of length L, so that it's sort of it's sending over a vector essentially that could be querying just like one bit, but it could be querying like all the bits. It depends on what the elements of that vector Q are, if they're ones or if they're zeros or whatever. And importantly, this query that the verifier sends over doesn't have to be ones and zeros. It can be other like terms that are in the finite field. So maybe the verifier sends over a vector that's like 3, 1, 0, -2, whatever. And so as a result, it's asking for the prover to send back a inner product of that proof with this query. Basically, an inner product just looks like this. It's the sum of the products between each bit of the proof and each element of the query vector. And so in this way, the verifier is querying some linear combination of the bits of the proof. And a linear combination of these bits could be a spot check if the query only consists of zeros and ones, and though they're precisely like lambda ones and everything else is zero. But in the case that the verifier wants to be more general and just like query some linear combination of the proof, then the prover will send over this linear combination, this like product. And this product, notice it evaluates to a single scalar in the finite field, and it sends it to not verifier 1, but sends it to verifier 2. So this linear combination of the elements of the proof is sent to verifier 2, and then verifier 2 chooses to accept or reject. Questions about this setup?
I'm trying to follow the distinction between verifier 1 and verifier 2. They're like two different people that you're trying to.
They're not two different people. They could be the same person. It's just that we're saying that they're V1 and V2. Like imagine just partitioning that person into two roles. The first role is the querying role, and the second role, V2, is the accept reject role. It's just to make it slightly easier, as we're going to talk about V1 and V2 in a lot more depth.
Okay.
And they could be separate people if they needed to be, but in this case, we don't have to think about that yet. So this is the procedure if the verifier wants to query one linear combination of the proof. What if the verifier has a bunch of linear combinations that they want to query? What if they have k of them? What if they want to query Q1 through Qk, different queries? The verifier can send multiple of these queries in a form of a matrix, which is a size L, which is the size of each query, times k. So there's k total queries, and each one has the length L, which is the length of proof. So that the verifier then receives this dot product of the matrix with the proof. And that dot product is the same thing as receiving k of these linear combinations. So this is just like matrix notation for the verifier receiving k of these linear combinations from the prover. And this way, the verifier gets to query k different linear combinations and get all of those back. This is basically like spot checking, but like more sophisticated, because now you're not just spot checking a few of the bits, you are spot checking linear combinations of all the bits. This is still okay, as you're not going to reveal the entire proof, because when you're spot checking a linear combination, it all gets summed together. It's not like you're getting like it's not like you're getting all the bits back whenever you query it. You're only getting like k terms back, whereas previously we had like lambda terms that we got back. In this case, it's just that these terms happen to give you information in a linear combination across the entire proof. And so in the diagram above, you can see that the proving system is the proof still takes as input everything as before, but it produces the proof where the first verifier will query an M matrix of queries, and we'll get back M dot product pi, where pi is the proof, as the answer from the prover. And then the second verifier will then output yes or no. So this is just another way of going about with the probabilistically checkable proof that is slightly more sophisticated. Now, this linear PCP that we will try to convert our R1CS program into, the reason we want to turn our R1CS program into a linear PCP is because in this case, we're able to take our matrices A, B, C, plug them into this proof, and eventually make our way towards the SNARK like we did before with the PCP, with like a Fiat-Shamir heuristic sort of thing. I'll give you some facts right now about what the linear PCP is going to look like. First, the proof size, pi, is going to be linear in the number of constraints in our R1CS program. So the more matrix multiplications in our circuit, the larger the proof size will be. But notice that this does not scale with the number of addition gates, which is good. And this means that it might not be the size of the circuit. It might be smaller than the size of the circuit. The runtime of the prover to generate this proof is also going to be linear in the number of constraints. And then the runtime of the verifier, when it's trying to come up with the queries, is going to be in linear in the size number of the constraints. And then this linear PCP we're going to construct will guarantee that if the prover is dishonest, meaning they don't know a valid witness, the probability that the verifier accepts a fraudulent proof is less than the number of constraints divided by the size of the finite field. This is important because it means that we have to pick a finite field that is large enough such that the number of constraints in our program is very small compared to it. So you'd want to like have like, a finite field where maybe you just have a very, very large prime and everything is modulo that prime, so that you know for sure that the number of possible elements in this field is much greater than the number of constraints in your R1CS program. And your R1CS program can be big. Like you could have tens of thousands of constraints in it because you have to prove very complicated things. So now that we've defined a linear PCP, we're going to try to build it. To build a linear PCP from an R1CS program, we're going to have to review some algebra. Okay. So before we get down to the grindstone of algebra, questions about this linear PCP setup?
So I'm wondering, here you're sort of defining the definition of what a linear PCP. I'm still trying to get the difference between a linear PCP and a normal PCP. And I guess the idea is a linear PCP follows these constraints that you just listed here. That's the difference.
And the linear PCP, the verifier will send queries that will touch possibly every single bit in the proof, because it's querying a linear combination of all the bits of the proof. Whereas before in a PCP, the verifier only got to touch the bits that it was spot checking.
Okay.
So in a PCP,
Gotcha.
you only get to spot check a few, but you don't get to see any information about any of the other bits. In this case, you get to glean a little bit of information about all the bits, but it's summed together so that you don't reveal the entire proof to the verifier. But this way, it's a slightly more sophisticated machine because this linear PCP could be built such that you are just spot checking. Like I said, if the query only consisted of zeros and ones, when it's multiplied together with the proof, it will produce a spot check. But it could be more sophisticated if you want it to be. And that way, the linear PCP has more proving power than the PCP did.
Okay, sweet.
So to build it, we must first review some algebra. The first algebra we got to review is actually one of my favorites, is about polynomial interpolation. And this is a theorem that is likely very familiar to all of you. We define a polynomial f that is of degree d in our finite field f. The polynomial interpolation theorem says that given d plus 1 points, we call them all alphas, alpha 0 through alpha d, within this finite field, such that we know f of alpha 0 through f of alpha d, meaning we know like what the polynomial evaluates to at these d plus 1 points. There only exists one unique polynomial that can satisfy this. Basically saying if we can identify d plus 1 points of a d degree polynomial, we know exactly what that polynomial is. There's only one possible polynomial that can fit that bill. There cannot be two different polynomials, and different here meaning that they have different coefficients in front of their terms. There cannot be two different polynomials that have the same values at d plus 1 points if both polynomials are degree d. So in the very simple case, let's say it's a degree 1 polynomial, like x plus 1, or like 2x plus 3, or whatever. If we have 2 points in this finite field, it's enough for us to define the line, essentially. That's what this theorem is saying. If you pick 2 points on the plane, you can only draw one line that passes through both of them. In the same way, if you were to pick 3 points on a plane, there's only one quadratic function that can pass through all 3 of them. If you pick 4 points on a plane, there's only one cubic function that can pass through all of them. That's exactly what this is saying. If you pick d plus 1 points on a plane, there's only one d-degree polynomial that can pass through them all. Raise your hand if you don't believe me, or make it known if you don't believe this theorem, because I will prove it to you very succinctly in the next slide. Okay, we don't have any doubters. Maybe I can just skip the proof, optimistically, move on. Actually, just because it's simpler, I would just go through the proof because I had to click the mouse anyways. The proof here is pretty simple. We need to find a unique polynomial, and to find a unique polynomial means to solve for what all these coefficients f0 through fd are. Here, we're going to define a slightly scary term, but this term is very, very benign, and we're going to use it again in the future, so it's good to define it now. We're going to define a van der Waals matrix. A van der Waals matrix is a matrix that has this following form. A van der Waals matrix with d elements, alpha 0 through alpha d, takes as its rows all the powers of alpha up until d, from 0 to d, and each of its alpha 0, alpha 1, alpha d occupy one of the rows of the matrix. So van der Waals matrix is just a very simple construction from a set of elements alpha 0 through alpha d. This van der Waals matrix we construct over here. And what we're basically trying to say is we need the product of our van der Waals matrix with a vector of the coefficients of our polynomial to equal the values that we are observing at each of those points, alpha 0 through alpha d. If we take a moment and walk through this matrix multiplication, we'll see that it makes sense. F0 times 1 plus F1 times alpha 0 plus F2 times alpha 0 squared plus ... all the way to FD times alpha 0 d, that is precisely equal to this equation evaluated when x equals alpha 0. And so this matrix multiplication is the same thing as evaluating the polynomial f at these points, alpha 0 through alpha d. And so we'd expect that if we had found a valid set of coefficients f0 through fd, it would equal the values on the plane of alpha 0 through alpha 1 through alpha d when they get plugged into the polynomial. So it's a very fancy linear algebra way of expressing that we have a set of coefficients such that these points get mapped to these points once they go through our function. Importantly, the fact that we've represented this as a set of matrix multiplications means that now we can invert the van der Waals matrix over to the right-hand side so that we multiply both sides by the inverse of the van der Waals matrix so that we are rearranging this expression over here into this expression over here, where we're saying that the coefficients that we're looking for are precisely equal to the inverse of the van der Waals matrix, the inverted van der Waals matrix, times the values that we've observed, f alpha 0 through f alpha d. The fact here that is very important that you have to take for granted is that the van der Waals matrix is invertible. You know that there's some matrices in the world that are not invertible, but the van der Waals matrix happens to be invertible. And that means that there always exists a set of coefficients, f0 through fd, satisfying this equation over here. Because you can always invert the van der Waals matrix, this expression over here on the right always has a valid output. And if you set your coefficients for your polynomial equal to the output over here, you will get a polynomial that satisfies these d plus 1 points being mapped to these. And there's only one such solution because this expression over here evaluates deterministically to one result. So essentially, by taking these d plus 1 constraints, turning them into a matrix and inverting that matrix and proving that the matrix is invertible, we prove that there is always a solution such that we have a polynomial that satisfies this. Very long-winded way of saying that picking 2 points on a plane defines a unique line. Picking 3 points on a plane defines a unique quadratic equation. But now that we've talked about this, we're going to talk about how it ties together very shortly. Questions about this polynomial interpolation and its proof?
Looks good. I guess the proof doesn't say anything about, there might be a lower degree polynomial that also matches the points.
In the case that there's a lower degree polynomial matching the points, that means that one of the coefficients here is 0. And that is still unique, because if there's a lower degree polynomial matching the points, that must mean that there isn't a higher degree one, I think.
Okay.
As long as these alpha 0 through alpha d are distinct. It's not like we picked a d of the same points. I agree, if we picked d of the same points,
Yeah,
then
that'll be
this
problematic.
would be degenerate. But yeah, assuming
Yeah.
that they're at different points, then yeah,
Yeah.
if it's just
Yeah.
happens to be a lower degree, then it's what it
Yeah,
is.
I'm just imagining picking like 10 points in a linear that a linear line fits to. And like it seems like you could put a higher order polynomial onto that as well. But it seems like it's not really relevant. I was just thinking about that.
Cool. So the second piece of algebra that we have to produce to aid us when we're turning into a linear PCP is the fundamental theorem of algebra. If you haven't heard of the fundamental theorem, don't worry. I didn't know that this was called the fundamental theorem either, but this is another one that has to do with polynomials. Let f and g be two polynomials of degree at most d, and let them not be the same polynomial. So they're not the same. Their coefficients are not the same. Then the probability that f and g evaluate to the same thing for a given point r is less than d divided by the size of the finite field for any point that we select in the finite field r. So it's saying if I have two random polynomials, in this case, say my polynomials are quadratic, so they have degree 2. The probability that some random point that I select on the plane happens to evaluate such that f of that point equals g of that point is less than 2 divided by the size of my field, which is basically like 0. In a similar, it's basically saying that 2 degree d polynomials can only intersect at most d points. That's the other way of putting this. It's like 2 lines can only intersect at possibly one point if they're not the same line. 2 parabolas, like quadratic equations, can only intersect at most 2 points. 2 cubic functions can only intersect at most 3 points. This is basically what it's saying. The probability that these two polynomials intersect at any given point is at most the degree divided by the size of the field, because they can only intersect at so many points.
Why is it less than rather than less than or equal to?
Yes, so because let me go through the proof, I guess. Maybe this is a typo. Let me go through the proof, and then we'll see if this is a typo or if it's intentionally less than. So the proof here is pretty fun, pretty elegant. We know that f and g are different polynomials. So let's take the difference of them. The difference of f and g will itself be a polynomial, but f and g, the polynomial will have degree less than or equal to d. It's possible it has lower degree than f and g themselves, because you're taking the difference. Maybe some of the terms have canceled out. And as a result, this polynomial that is the difference between the two can only have at most d roots, or d points where the polynomial evaluates to 0. That means that there's only d possible spots where f of x minus g of x equals 0. And that means that there's only d possible spots where f of x equals g of x. And that means that there is at most d points out of the finite field where f equals g. So I think in this case, you're right. We have a less than or equal to over there. It should be less than or equal to instead of a strictly less than. So this proof uses the fact that the polynomial that is the difference has a somewhat limited degree, which is less than or equal to d, and thus there can only be d spots where that could evaluate to 0. And that means that there's only d spots where these two polynomials can equal each other. And that's d points out of all the elements of the finite field. Okay, we're done with the we're done with the algebra, or we're done with the tools that we're introducing. It's just those two tools: polynomial interpolation and the fundamental theorem. So now let's go back to our construction. To go from our R1CS program to our linear probabilistically checkable proof, let's first remember what our R1CS program looks like. It has 3 matrices A, B, and C. We have our public information X, private information W, and we define our input vector as Z with a 1 in the front, then our public information X, then private information W. And we wanted this to be true. We wanted this evaluation of the expression A matrix multiplication Z, element-wise multiplication with B matrix multiplication Z equals C matrix multiplication Z, where all 3 of these terms, A, Z, B, Z, and C, Z, are vectors of size M. M, again, being the number of constraints in our R1CS program. So Z being the input vector, these are the matrices, and there are M constraints. To turn this into a linear PCP, what do? Let's start with defining a polynomial. Surprise. Let's define a polynomial F by interpolating this matrix, this vector A, Z, which we said is length M. Let's interpolate it at M different points, meaning that we have, by taking this term over here and using it to evaluate the polynomial at M points, we have uniquely defined one possible polynomial of degree M-1. So this f of x is that polynomial of degree M-1 that satisfies this expression at all M points for A, Z. Questions about how this construction works? It's saying that like we have multiplied our matrix A with our vector Z. We've gotten back some vector of length M, meaning we have M elements there. Let's take each of these M elements and say that f of 0 equals the first element, f of 1 equals the second element, f of 2 equals the third element, so on and so forth, until we have M different points that are chosen based on what we had over here. And there's only one possible degree M-1 polynomial that can evaluate in this way. And notice that we are just arbitrarily allowing the, so these are the y values of our polynomial. These are the x values. Notice that we're just arbitrarily letting the x values be the values 1 through m. We could have picked the x values to be -1 through -m. It doesn't matter. We could have picked them to be 2, 4, 6, 8, whatever. We could pick whatever we wanted for these x values in our polynomial, but we just, for simplicity, picked 1 through m to be the x values. So we first construct this polynomial by interpolating them. We're going to define a second polynomial that does the same exact thing, except with the second term, B matrix multiplication Z. Same exact procedure as the first, except now we're interpolating it such that it takes on the values of B times Z at these M different points. So it's going to be a different polynomial, but it's still going to be degree M-1. And then finally, if you thought we're going to do the same thing for C times Z, you're correct. Except we're doing something a little bit more complicated than just doing this for C times Z. We're defining a third polynomial H that interpolates these M points from C times Z, but in addition also takes on the values f of I times g of I for M more points afterwards. You're gonna see why we need to do this extra sort of interpolation afterwards. But it means that because we have to interpolate at 2 M points, this polynomial H will have degree 2m-1 instead of m-1. And we're gonna need this H to take on these extra values because we're eventually gonna have H being set equal to f times g. Here, the way we define f, g, and h, we're successfully able to say that h equals f times g is equivalent to what we had wanted before, which is a times z matrix element-wise multiplication b times z equals c times z. This being true is exactly the same as this being true. So maybe saying, Bill, why do we need to do the extra interpolation here of these points? It's because when you multiply 2 degree M-1 matrices together, you can't just evaluate that to another n-1 degree polynomial, two n-1 degree polynomials together will multiply to get you degree 2m minus 2 polynomial. But I guess in this case, we have defined it as 2m minus 1. Essentially saying that like when we multiply these two together, we need a larger, we need a higher degree polynomial over here. I think this is going to end up becoming 2m minus 2 after we're done doing a few more manipulations. So suspend your disbelief right now about like why these 2 degree m minus 1 polynomials somehow add up to 2m minus 1. Suspend your disbelief for just 1 second here. But the gist of it is that we need this h to be twice the degree of both of these guys, so that these two polynomials can multiply together to become h. Questions about this first step in the conversion?
I'm thinking, you're saying it will manipulate and it'll maybe turn into 2m minus 2. Is it not maybe already 2m minus 2?
It could already be degree 2m minus 2, that's right. But it could be degree 2m minus 1. We don't know, because
Okay.
we need to we need to satisfy these constraints at 2m different points. And so it's possible it's degree 2m minus 1. It might end up being degree 2m minus 2, but we don't know that for sure yet. We will know for sure in a little bit though.
All right.
So the next step here is, once we have figured out what these polynomials are so that we could evaluate this expression in an equivalent way, h here we say is unique. That's pretty easy to just see, because like, based on this expression and the constraints that h has to satisfy, there's only one h that can do the job. And now how do we proceed from here? The idea here is that the verifier will try to check that h equals f times g by spot checking at m-1 random points r, because we had seen with the fundamental theorem of algebra that the probability that these two are equal if the polynomials weren't equal is very, very small probability, 2m-1 divided by the size of the field. The only way that spot checking all of these points would lead to all of them being like h of x equals f of x times g of x is with high probability that h actually equals f times g. So in this way, we're now doing some spot checking, just like we did with the original Killian SNARK. We're doing some spot checking, except we're doing spot checking with these polynomials. We're spot checking this polynomial h, and we're spot checking whether it is equal to these two polynomials multiplied together at these different points r. And so if we were to write this all together, it would be that f of r is equal to, again, sort of like a Vandermonde matrix style notation of r raised to a bunch of the powers times the coefficients of f. And this we can rewrite in a slightly more complicated manner to say that these coefficients f, remember from our slide on linear interpolation, these coefficients f can be written as the inverse of the Vandermonde matrix times the values of f at the points we had interpolated on, which are precisely the points 1 through m. So we've taken this set of coefficients and we've rewritten them using the Vandermonde matrix and using the values that we were interpolating on, f1 through fm, which are exactly az1, az2 through azm. And so we can, as a result, rewrite this vector as a times z. And so you can see we've rewritten the evaluation of our polynomial f at point r to be this times the inverse Vandermonde matrix times a times z, which finally we can take everything in blue and squish it all together into a term we define called Q1. And so suddenly we have the first linear combination query of our linear PCP. The linear combination of z being our input vector, remember z being like the proof that gets sent over essentially. We have z as the proof getting sent over, and the linear combination of the proof ends up being the inner product of Q1 times z where Q1 is this whole big mess over here. And so if we're able to turn this polynomial evaluation at point R into this linear combination of the elements of Z, this gets us one step closer to representing this whole thing as a probabilistically checkable proof. Now let's repeat the same thing with BZ, which was accompanied by our polynomial G. The polynomial G can be constructed in the exact same way, except now we have a matrix B over here instead of A. And so this will be a second query, or it's a Q2 over here, a second query, inner product with Z. Questions about how we have suddenly turned our polynomial evaluations into inner products? So we're saying we're now able to evaluate f of R and g of R as inner products of some queries Q1 and Q2 with the input vector Z. Now we're saying, okay, Bill, what about H? What about H? Where's H of R? H of R is going to be slightly more complicated, but not too much more so. The thing about H of R is that because it has degree 2m-1, well, first, this first term over here has to have 2m-1 terms in it instead of just m-1. This Vandermonde matrix is suddenly a bit bigger, and we can't just take the vector. We can't just take the matrix C. We have to append an identity matrix of size m afterwards, so that together these evaluate to the correct dimensions. So we have the matrix C that was on the right-hand side of the equation, concatenated with some identity matrix, and that way we can evaluate it multiplying it against Z, which is our input vector, as well as the other points we had interpolated on. These other points being h of m+1 through h of 2m, which were supposed to be equal to f times g at these points. So you can see that we had to make all these matrices a little bit bigger to accommodate for the fact that h is of size 2m-1 instead of just m-1. And so the resulting inner product that we get is of this part in green, which is Q3. This is the vector. But on the right-hand side, we don't just get the Z. We don't just get to use the input vector Z. We need to use input vector Z concatenated with these extra points that H interpolated on. And so basically what we want now is the verifier wants to check using 2m-1 random points R. It'll spot check that this equation is true, which means spot checking that this equation is true. And suddenly we can see that spot checking these random points R involves querying some linear combinations of stuff, which is exactly what our linear PCP is good at. Questions about this transformation? Oh boy, I might have lost everyone.
Yeah, I think for me, I was doing good till like these last two slides, and then a bunch of stuff came together, and now I think I need to. I don't know if I have other people there, but I think I just need to take more time to look at these slides and look back at previous slides and connect everything together.
Yeah, I'm feeling the same way.
I think the big takeaway here is that you're able to represent your polynomial
using
an
big
inner
takeaway
product.
was helpful last summer, yeah.
Right. You've converted your polynomial into an inner product, your polynomial into an inner product, and your polynomial into an inner product when you're evaluating the polynomials at some point R. And we're going to do this for some random points R, so that we're basically spot checking that these polynomials are equal to each other, which is the same thing as spot checking that these inner products are equal to each other, which should be sufficient to spot check that the R1CS program was built to evaluate to 0, which is equivalent to spot checking that the arithmetic circuit was built correctly to evaluate to 0. This is how I built the spot check. At the end of the day, it's all a spot check. So now we've talked about how all of these inner products have to use Z, which is the input vector, right? And the Z here would be in our linear PCP what we naively send over. It would become our proof. We could just send over Z as our proof. But remember that there's one big problem here, which is if we want to ever make this a zero knowledge SNARK, we can't let the proof contain the witness. We can't send the witness over to the verifier. So how are we able to do this inner product stuff, these linear combinations of things, if we can't send the witness over? If the verifier cannot decide what queues it needs, what queries it needs? The solution is a bit complicated. We split each of the queues from the previous page, each of the queries, into a left-hand side and a right-hand side. The left-hand side of each query contains the first k+1 terms that correspond to all the things that depend on public information. And then everything on the right-hand side is what depends on the private witness information. Okay, so we've just split each of our query vectors into two parts, left and right. This way, qi inner product with z is the same thing as qi left-hand side inner product with 1 and x, this left-hand part, plus qi right-hand side inner product with the witness, the right side. And the linear PCP can now become something that keeps the witness from ever being sent to the verifier. The prover sends, okay, sorry. This is an intermediate step where you have to suspend your disbelief because it says here on the screen, I know it says that the prover is sending over the witness, but in a moment we're going to encode everything. In a moment we're going to encrypt everything. But basically the prover sends over the witness as well as these extra interpolated points to the verifier v1. The verifier sends 3 queries over, again for like q1, q2, and q3, and the prover sends the results to verifier v2 for q1 right-hand side only, inner product with the proof, q2 right-hand side only, inner product with the proof, and then q3 right-hand side only, inner product with the proof. So the prover is actually only sending over the stuff that is a query that is of private information. Why does it only end up sending over the right-hand side? Why does it not send over the stuff that relates to the public information on the left-hand side? It's because the verifier can just do that inner product itself. Because the left-hand side is not sensitive, the left-hand side isn't secretive information, the verifier can just do that inner product itself. And so the verifier can check that this inner product of the left-hand side plus A, which it received from the prover, times the inner product of the left-hand side plus B, which it received from the prover, equals the inner product of the left-hand side times C, plus C, which it received from the prover. So in this way, the verifier will have to do this computation on the public information itself, but it will trust the prover for the parts that depend on the private information, which is the witness. So in this sense, it is like our previous Killian SNARK, where the proof does get sent over, but the verifier doesn't actually look at the proof. This proof being sent over is a way to commit the prover to this proof. And so when we make this non-interactive, this proof isn't going to end up being sent to the verifier after all. And so this witness is going to stay private. But the point of this construction here is to commit the prover to its proof, because once the prover sends a proof over, it can't change it anymore, you know? But then the verifier doesn't actually look at the proof. The verifier asks the prover these 3 queries, and then the prover sends over the results for the queries A, B, and C. And then the verifier takes those A, B, and C and plugs it into this inner product expression with the information that it does know publicly to check that the prover was honest and to check that the prover has a witness. So questions about splitting this set of queries up into left-hand side and right-hand side parts.
So in this case, verifier 1 has to be a trusted setup verifier, like they have to be trusted essentially.
In this current construction where it's interactive, yeah, you have to trust verifier 1 doesn't look at the proof that it's being sent. But in a second, we're going to make this non-interactive, and at the same time, we're going to make it trustless.
Okay.
Yeah, because remember, right now it is still a probabilistically checkable proof. It's a PCP that is interactive, and it has not turned into a SNARK yet. The last step, which I've bolded here, is to turn this linear PCP into the SNARK. And so if you remember what we did with the Killian SNARK, you're going to see that a similar vein of logic will appear here, which is, let's make this non-interactive so that we can hide the private information that is the witness. And I know we're out of time, so I guess we're going to continue this in London with part 6. I have high confidence that we will finish in part 6.
All right.
Awesome,
Yeah.
guys.
Let me know what questions you have before we end it today.
Yeah, I think on my side, I mean, it's a look and map on those last few slides you're talking about. There was a bunch of stuff coming together. I got to map it back to previous slides. But sweet.
Yeah, and I mean, walking through this one time is instructive. Remembering this in your head for all of eternity is not needed. I think even just knowing that if you like, you have these slides in your hands, like, or on your computer, right? Whenever you do need to learn, like get a refresher, feeling like you can walk through the slides and in like an hour be able to get back to where you are right now. I think that is the goal you want to get to with this content, because you've walked through it once, you get the gist of it, and whenever you are, need to work on snarks in the future, if you feel like you can come back to these slides and get back up to speed in an hour by like looking at the slides and remembering what I said, that's good. That's good.
Yeah, for sure.
And the recording is there for all eternity.
Yes. Yes.
All right. Awesome. Thanks, Bill.
Yeah. Thanks, everyone. And I guess Amy and I will see you all in London next week virtually.
Awesome.
Thank you.
All right. See you guys.